Welcome everyone, lecture number 23. Today in this video lecture, I will tell you second application of Laplace transform in solving ordinary differential equations with variable coefficients. So let's quickly take one example to understand the concept. Example is we have the given differential equation y double dash t plus ty dash t. Here the coefficients are variable, not constant. Constant case I have discussed in my previous video. You can go to lecture number 22 for that. Y0 is equal to 0 and y dash and y dash 0 is equal to 1. So here you can see the coefficient of y dash is t, which is a variable, and we are given these two initial conditions. So as usual, the method of finding the solution is same. We take the Laplace transform of this equation, both sides. Laplace transform of the given equation. We get Laplace transform of y double dash t plus Laplace transform of ty dash t plus Laplace, sorry, it is minus sign. So let me correct. Laplace transform of yt. So we apply the property of Laplace transform. So Laplace transform of derivative property. So by that property, the value of Laplace transform of y double dash t is p square. Laplace transform of yt minus py at 0 minus y dash at 0 plus because we have t here, so by the property of Laplace transform, whenever a function is multiplied by t or powers of t, its Laplace transform is, let me tell you the formula. Laplace transform of t and ft is minus 1 raised to the power n, nth derivative of the function with respect to t. Okay. So using this property, we have negative sign here because the power of t is 1. So let me use the negative sign here, and d over dp into Laplace of y dash t minus Laplace of yt is equal to 0. Now applying the initial conditions, we are given applying initial conditions, we get, let me do it on the next page, p square into Laplace of yt minus y at 0 is 0, so this term disappear, and here it is 1, so it is minus 1. Okay, minus, we have d over dp of Laplace of y dash t. So we substitute the value of Laplace of y dash t first. D over dp p into Laplace of yt minus y at 0 minus Laplace of yt. Okay. Now p square Laplace of yt minus 1 minus Laplace of yt minus p. We have to use the product rule here. P into Laplace d over dp of Laplace of yt minus derivative of p is 1, so it is simply Laplace of yt, and y at 0 is 0, so this term is 0 is equal to 0. Now we can take Laplace of yt common, collecting the coefficients of Laplace of yt. We have p square, and this is minus 2 Laplace of yt, so it is 2. So we have minus p d over dp of Laplace of yt minus 1 equal to 0. So here we have p into p into d over dp, p into d over dp of Laplace of yt minus p square minus 2 into Laplace of yt. If you look at this equation very carefully, it will be minus 1. Okay. So you can see here, if I use the notation, suppose y bar for this, and I rewrite this again, then this will be look like this. Minus p square minus 2 y bar okay. So here I forget to tell you that I have changed the sign here after this line. So there, here we have positive sign. Okay. So now uh, if I divide this whole equation by p, then I will get the equation which look like this: dy cap over dp minus p minus 2 upon p y cap. See? Okay. So here, if you look at this equation, this is a linear differential equation type, which type is dy over dx plus py is equal to q. You have this type of equation, and p should be the function of uh, x. Okay, here p and q both are the functions of x. So I have this p and this q, and both are functions of p. So to solve this equation, we have to find integrating factor. So integrating factor is defined as e raised to the power integral p dx. So I have p d by dp here, because in place of x I have p here. So the value of p is, we have to include this negative sign with p. So value of p is 2 upon p minus p. Okay, and the integration is with respect to p. So this value is e raised to the power 2 log p minus p square by 2. So I have e raised to the power log p square minus p square by 2. So I can write this as p square into e raised to the power minus p square by 2. Solution of this equation is solution of the above equation is, what is the solution? Y bar into integrating factor is equal to Q into integrating factor dp plus C. So one of the p will cancel, and we have minus p e raised to power minus p square by 2 dp plus C. So we can take this as t. We can suppose as this as t. So if I take this as p, I'll get p dp is equal to dt. So the integration of this function is minus e raised to the power minus p square by 2. Okay. Sorry, one of the negative sign will come, so it will be positive, plus C. Okay, we'll write plus C. So the value of y bar is 1 upon p square plus C upon p square e raised to the power p square by 2. So you can open this exponential function, expand this 1 plus p square by 2 e raised to power x का expansion होता है 1 plus x square upon factorial 2 plus x cube upon factorial 3 and so on. Here using this formula, we have 1 plus x square upon factorial 2 and so on. Okay, so this is, you can add these two terms, c plus 1 upon p square plus c upon 2 plus 1 upon 8 cp square and so on. Okay, so this is nothing but we have Laplace of yt here. So by um, Taking the inverse Laplace transform at this stage, ILT, both sides, I'll get yt is equal to c plus 1 is constant. So Laplace inverse will work on 1 upon p square plus c upon 2 is again constant. Laplace inverse will work on 1, and 1 upon 8 c is constant. Laplace inverse will work on p square, and so on. Ahead of this term we have all the positive powers of p. Okay. So now there is one result. You remember this result. The result is Laplace inverse of positive powers of p including 0, where n is 0, 1, 2, 3, and so on. For all these powers of p, Laplace inverse is always 0 of any uh, uh, expression of the type p square or p or simply 1. Okay. So including this term, all the terms ahead of this term will be 0 because of this result. सारी टर्म्स की वैल्यू 0 हो जाएगी क्योंकि सबका लाप्लास इनवर्स 0 हो जाएगा इस फॉर्मूले की वजह से. So what is left here is only c plus 1 into t, because Laplace inverse of 1 upon p square is t. So the value of yt is c plus 1 into t. Okay. Now to find the value of c, we can use the condition that is given to us that y0 is 1. Okay. So we can substitute. What we do here is, first of all, we differentiate this and we will get c plus 1, and then we put 0 at place of t, so that we have only c plus 1, and here we have 1. So the value of c is 0. This implies yt is equal to t. That is the solution of the given equation. Okay, I hope you understand this, the method of solving uh, ordinary differential equation with variable coefficients using Laplace transform. Okay, so you try this question that I am going to giving you. You can try this. Solve t y double dash t plus 1 minus 2t y dash t minus 2yt such that y0 is 1 and y dash at 0 is 2. Okay. Again, I am repeating the question. T y double dash t plus 1 minus 2 t y dash t minus 2 yt is equal to 0, such that y0 is equal to 1 and y dash 0 is equal to 2. Please try this question, okay, by yourself. Thank you for watching the video, and if you like my video, please press the like button, share my video, and don't forget to subscribe my channel if you have not subscribed it. Okay, thank you so much.